Okay, so the final talk for today is estimation of group action with energy constraints by Masahito Hayashi.
Thank you, Chairman. Today I want to talk about estimation of group action with energy constraint. Usually, many people interested in the quantum methodology. In that case, we have square speed up. But in that topic, existing paper never discussed with energy constraint. So in this topic, in this talk, I want to discuss that topic with energy constraint. But also in that case, in order to treat this problem, I consider a formulation of estimation of group action. Essentially, this one is estimation of unitary action, but in order to use the group structure, we assume that group structure. So this is slightly strong restriction, but we can derive the very tight evaluation. So this is contents. Firstly, we give a brief summary of estimation in group covariant case, and we formulate the estimation of group action with average energy restriction, and we give the practical construction of asymptotically optimal estimator. And also, if we have time, we apply the application to the energy uncertainty relation of Robertson type. So firstly, this is the formulation of our group action. So in that case, we firstly consider a projective unitary representation F of the group G on Hilbert space H. So in that case, we consider input state, and there is an unknown unitary to be estimated. This is unknown unitary. G is the element of group, and also we apply measurement. Then we obtain some estimate. So in this setting, we have two choice, two kind of freedom. So one is a choice of input state. Another one is a choice of measurement. So we optimize both choices. This is our operation. So and also in that setting, we consider error function. In order to employ the group structure, we assume that this group invariance. So this is through parameter G, and this is estimate. So this one is the outcome. This is a real value, and we assume that this group invariance property. And also, under this error function, we consider average error when the parameter is G, when the true parameter is G. So in that case, we consider average of this error function, and this is the distribution of the output G hat. So the input is low, and this is a true unitary Fg, and our output measurement is this one. So in that case, this one gives the output distribution of the estimate G hat. So, but of course, we don't know the true parameter G. In that case, we consider two kind of formulation. One formulation is Bayesian, another one is minimax. So Bayesian case, we fix the prior distribution, and we take the average under this prior distribution. And usually we consider invariant measure as a prior, and also we consider minimax. Minimax case is the worst value of the this error, average error. So now we explain the group covariant measurement. This is originally introduced by Professor Horebo many years ago, before Schwarz factorization. So there is this one. So Hilbert space and group G and representation. So a POVM taking values E is called covariant. Is if that measurement satisfies this condition, covariant condition. So this is arbitrary G, and application of this G is equal to this one. B is a set of outcome, so subset. So in that case, we call the covariant, and we now we consider a set of arbitrary POVM taking values in the group G, and also a set of covariant measurements. So for any measurement, is included in the covariant. A measurement is included in the covariant if and only if the measurement POVM satisfies this condition. There exists that operator T satisfying this property. So this is the necessary and sufficient condition for the covariant measurement. Covariant measurement very important because we have our optimization problem reduced to the only for the covariant measurement. So firstly, we consider minimax problem. In that case, we can choose the optimal input and optimal measurement M. So, but in that case, also we consider mu. Mu is the invariant measure on the G. So, and invariant prior is G, and we consider base prior, base average, and minimax average. And also in this case, we consider minimization under the choice of input state and outcome P of M. But that problem reduced to this way. So we can restrict rho is pure and M is a covariant. And also our problem reduced to this way. So our measurement of mu and this one is pure, also the Bayesian case. So essentially the solution of the Bayesian is same as the solution of the minimax in the covariance structure. Also, but in that case, we assume that G is compact. G is not compact. In that case, we cannot consider that invariant measure. In that case, we can only consider minimax case. So now, in order to treat this problem, we employ the method of the Fourier analysis. So we explain the Fourier analysis. This one is very mathematical, but this is very important. So G hat is a set of irreducible unitary representation. Of course, if G is a usual commutative group, in that case, essentially G hat is a usual Fourier transform. But if G is not commutative, in that case, each representation is not one dimension. So we have some difficulty, but depends on the and also depends on the level of the unitary representation. We have a irreducible representation V lambda. V lambda is a representation space, and we consider a set of Hilbert-Schmidt operators on this irreducible Hilbert space. So and also we consider that direct sum of that Hilbert-Schmidt operators. So the Fourier transform given this one. So firstly, we consider L2 function on the group G and convert to the that space in this way. So f is a kind of the wave function, and we take this one. This one is for each G. So for each lambda, this one gives a matrix on the this Hilbert space, on the Hilbert space, and we have to consider its direct sum product. So there is a matrix, and we have that direct sum product. This is our notation, and also we consider its inverse map. This one is called inverse Fourier transform in that way. So essentially, this tool is very, very important for the following discussion. So now we consider energy constraint. What is the energy constraint? H is Hamiltonian, and dr is so under this one, so we introduce this quantity. So x is something with input pure state. Input pure state can be described by some matrix in the sense of the previous sense. So because this element corresponds to the pure states, so that pure state corresponds to x. So and f inverse is a Fourier transform inverse, and considering that this one gives a distribution of estimate of the G hat. So this is distribution. So and also we consider its average. So in that case, finally our target is reduced to this way. So originally our problem is this one. So this is input state. This is P of M output, and we consider that energy constraint. This one is minimax problem. Also, we can consider same problem under the group covariance. So this one is the same. So this one is covariant measurement. But this problem reduced to this one. So essentially same. So dr is the only mathematical symbol, but it is enough to consider this minimization. So this one is energy constraint, and this one x is a kind of the input state, and we take the minimum under this condition. So it is enough to consider this condition under that energy constraint. So For example, now I want to consider very, very simple case. We consider action of the group G. So in that case, usually we consider this error function. This is through G, and this is estimate. And also our representation describes this one. So each lambda, we have this unitary one-dimensional unitary representation. And also we consider energy. Energy is a q square. So lambda corresponds, in that case, G corresponds to the, momentum, and energy corresponds to the q square is position. So in that case, we consider that problem. So average energy is this one is smaller than this one, and also we minimize this one. But this problem mathematically converted to this problem. This is a usual Fourier analysis. Very, very easy problem because this is usual Fourier transform, and this is the original function. So as you know, this problem converted to this one. You know, this problem is very, very easy because the usual minimal uncertainty relationship. So as you know, that the solution is equal to this one. So the minimum minimum performance is attained by this wave function. So, but this is very surprising because the energy only behaves the inverse of E, not square. So this is the problem. So usually, sometimes you consider that quantum methodology. In that case, that minimum error behave square inverse of square. But in this problem, we consider square energy behave the square of position. Due to this condition, that one is behave only this way. So also we want to consider estimation phase error, and also we consider estimation application of SU2 or SO3. So in order to treat that compact Lie group, so we need to employ Mathieu function. Mathieu function is the following. So firstly, we consider periodic differential operator, this one. So using, of course, it is quite difficult to solve this minimization problem. But that minimum eigenvalue is known as this way. So depending on this parameter Q, that minimum eigenvalue is mathematically known. It is quite difficult to calculate this one, but if you use the Mathematica or Maple, so that software automatically calculates these functions. Also, that eigenfunction is quite difficult, but it is known as a very special function. So we can calculate this one by using a Mathematica. Also, this is a space of this one. So in the following discussion, we employ these two tools. This is very important. So next, we consider estimation of unitary group 1. So in that case, we consider this error function. Here is G hat. So we consider this one. So why we consider this one? Because our problem is periodic. So you cannot consider G minus G hat. We have to consider periodic function. And also, in that case, our group action is one dimension. And in this case, reducible representation, this one, and energy Hamiltonian given this way. So in that case, that one is original problem. But this problem converted to this one by using a Fourier analysis. And this problem can be solved by this way, by using the Mathieu function. So optimal input constructed by using that Mathieu function. Of course, in that case, if we go to infinity, so we have an asymptotic expansion, and also this asymptotic behavior only inverse of the E, not square. So this one is different from usual quantum methodology. And this one is that graph by using a Mathematica. So we can directly calculate this graph by using a Mathematica. So finally, next we proceed to the estimation of SU2. SU2 case is slightly difficult. So we consider this error function. So this one is different from the gate fidelity. In the case of gate fidelity, you cannot distinguish application of SU2 1 and -1. So in that case, in the case of the gate fidelity, it is suitable to consider the action of SO3, not SU2. So in order to consider the estimation of SU2, we need to employ this error function. So in that case, we also consider what is this? This one is Hamiltonian. So this one is a very famous. What is this? Casimir operator. So this is very physically natural. in physics. So in that case, so essentially we consider have this problem, this function space, but this function space reduced to the this function space. Then using this relationship, so our original problem is this one. So we input some irreducible components, and we consider minimize the P of M, and under this energy constraint, we minimize error. But this one mathematically equivalent to this problem, and also solve this one. In that case, that optimal value can be described by using the Mathieu function, and that minimum behave this way. So this one also behave inverse of the energy, not square. So similarly, we can numerically calculate this graph in the case of SU2. And also, next we want to consider a factor system of the projective, because in the case of SO3, we need to consider projective representation, because in the case of half integer representation, we don't have the representation of the SO3. We only have the projective unitary representation of SO3. So in order to treat that case, we have to consider factor system. So using this one, so we have a similar result. So essentially, that modification is obtained by Professor Giulio Ciribella. So in that setting, so we consider this one. This is essentially same as gate fidelity. So gate fidelity, in the case of gate fidelity, it is suitable to use the SO3. So in that case, our Hamiltonian is this one. This is Casimir operator. And also, in that case, we consider this represented space, but this one converted to this one. Then our minimization problem of the under the energy constraint of the that error function, this one converted to this one. This is integer case, and this is half integer case. So sometimes 1/2 or 3/2. So and this is integer case. This is in that case, this is projective representation. So in the integer case, this problem is completely solved by this way, and also half integer case solved by this one. So this is graph. So in the half integer case and the integer case, this one is integer case, and maybe this one is a half integer case. Sorry, thick line is a projective case. Thick line is projective. This is projective means half integer. Thick line is half integer, and the normal line is integer case. So finally, we proceed to the Heisenberg representation. In that case, our Hilbert space is this one, but in that case, we need some multiplicity. So in the multiplicity also written as this space, but only that group acts on this first space. So in that case, we minimize. It is enough to consider this quantity, and our energy constraint described by this way. So in that case, similarly, the minimum value described by this. So how to solve this one? So essentially, we only choose the coordinate by using the unitary. So then, similarly, essentially, that problem is solving the, how to say, minimum uncertainty relationship. So the problem is not so difficult. So essentially, that problem reduced to this way. So it is enough to consider uncertainty relation. Then the minimum error is behave this one. So how many minutes? Oh, 10 minutes. Oh, now I want to explain how to realize that's optimal performance. This is more important topic. So in the case of U1 case, in this case, it is enough to consider only one copy repetition of the one copy case. So now we consider this some input state, and this is unitary, and we apply optimal measurement on the on one system. So and we repeat the same process so any times, and after that we apply maximum likelihood estimator. Then we obtain this one. This is very trivial, not so difficult process. So application continuing this one, so we can attain the optimum performance. How to say? What is optimal performance in the sense of the first order? So in the case of the estimation of U1, the optimal coefficient is 1/2. 1/8. So how to attain this first order? So usually we have to consider very big system, and we consider optimization on the very big system. But we don't need such a process to realize the only first order optimality. In that case, it is enough to consider only two-dimensional system, and we prepare one input state, usually one input state, and we repeat the same that process so many times. Then the total energy is E, and also that minimum error, that mean square error behave only the optimal way. So this method attains the optimum performance. In this case, we don't need any entanglement. So also in the case of SU2, we have a similar property. So in that case, it is enough to consider usual representation. So, but in that case, we have some restriction because in that case, we need to prepare that support contains the integer case and half integer case. Because if you only have the integer representation, for example, if you have only one half representation, in that case, you cannot distinguish 1 and minus 1. So in order to distinguish 1 and minus 1, so you have to prepare two kind of representation. So maximal weight is 1/2. For example, maximal weight is 1/2 and 1. So in order to consider that two kind of representation, and the input is its superposition, in that case we can distinguish 1 and 1 minus 1. So if we prepare that kind of state, so and we repeat the same that process so many times, and we apply MLE, then we can attain the optimum performance in the first order coefficient. So also in the case of SO3, in that case, it's very easy. So it is enough to consider one half case, so two-dimensional system, or three-dimensional case. The maximum weight is 1. So it is enough to the only single representation. So phi is a single representation, single derivative representation, and you apply unitary, and we apply covariant measurement, and we repeat the same process, and we apply MLE from the n data. Then this method attains the optimal performance in the first order coefficient. Also, what is this? Sorry. Okay. So then, in that sense, so we don't need any entanglement. So entanglement never enhance the quality of estimation in our setting. So this is a message. So finally, we want to apply our result to the uncertain relation. So usually we consider uncertain relation on the Hilbert space L2R, but now we want to consider that periodic system. So we consider L2 function on the L2 function on the U1 or L2 function on the S1. So periodic function. So under that periodic function, we define the square error is this one. So Q is that's usual operator, but we consider this one and this one. And also we can similarly define the moment operator by using the by using the differential. So then we can consider square of the variance of the that momentum. So under this condition, we can minimize this one. But this problem is completely the same as the previous estimation problem. So that's minimization exactly solved by this way, by using the Masahito function. So, and also that minimum is realized by this wave function. So similarly, we can consider uncertain relation on the L2 S3, not S2. So we cannot, in our method, we cannot consider S2. Only we can consider S1 and S3, because S1 and S3 has a Lie group structure. S2 don't have any group structure. This is a kind of the demerit of our method. But under this method, we consider this function, and we can define square error of the position operator and square error of the moment operator. So momentum has there is a three kind of the coordinate, and we consider that to be square and this one. Also, this error has a invariant structure. Under this condition, we can minimize this one. But this problem is completely the same as the previous group action problem. one is completely solved to this one by using the Mathieu function. So this function by realizing the function realizing the minimum is given by using this Mathieu function. But unfortunately, this one is only one parameter. So in order to realize the minimum uncertainty, we have to consider relationship between the that relationship I skip, but there is some relationship between that function and this one. So this one is slightly complicated. Anyway, we can completely solve that optimal solution, optimal problem, optimization problem. Then this is a conclusion. We have proposed a method with inverse Fourier transform as a unified approach for the estimation of group action. So using this method, we have derived the optimal estimator with energy constraint in several groups. And also, we have shown that the entanglement of input and output cannot improve under the energy constraint. We also have apply our result to the uncertain relation. Thank you very much.
So, any questions? So, one question I have is that the examples that you described throughout the talk are all continuous groups. Are there any interesting examples with discrete groups?
Yes, of course, discrete group is possible. Yes, for example, so because yes. So in this case, G is U1 and G hat is Z. But if G equal to the integer Z, in that case G hat is U1. So in that case, maybe we have a similar result, but maybe slightly difficult to because in that case, so G hat if integer case G hat is U1. In that case, quite difficult to consider energy constraint. Of course, we can apply this kind of Fourier analytic method. This is okay, but that energy constraint is slightly difficult because why we consider energy constraint? Because the set of the irreducible space is not compact. So in order to consider that situation, we employ this one. But if the group is discrete, in that case, maybe G hat is a set of representation is compact, I think. So maybe slightly different method is required for the constraint. But of course, we can employ this Fourier analytic method in the case of a discrete group.
Okay. Thank you. Any question just here?
So
yes.
When your cohort spaces, the ones that the group is acting on,
Yes.
are representation spaces.
Yes.
When you conclude that entanglement is not useful,
No.
what tensor product factorization would entanglement appear in? What would be entangled with what?
Maybe in the optimal case, that optimal input has small entangled, but without entanglement, we can attain the almost same property, almost the same quality. So, of course, optimal state has maybe small entangled, but how to explain that solution? So, your question. Could you explain?
Well, so it seems like the spaces, the Hilbert space that you're acting on, that the group acts on here, is sort of monolithic. I'm not clear how you're dividing it into Alice and Bob, or Alice, Bob, and Charlie.
No, of course, yes, of course, yes, of course. In that case, of course, not Alice and Bob. There are so many copies. Usually, okay. How to describe this one? So, for example, we consider this one. So, in that case, there is some entangled. So, there is any system. So, we can consider entangled. So, tensor product. So, behind the tensor product. Then we can consider entanglement between the copies system. But in that case, of course, you can consider the entangled input, but that entangled input almost does not enhance the quality.
And maybe one more question right at the back.
All right, I have a conceptual question.
Yes.
So if I understand it correctly, you are applying the energy constraint on the probe state only. So I was wondering if you shouldn't also have an energy constraint on the measurement.
Measurement. Of course, I don't care about measurement in that setting. Sorry. Yes.
So there is, I mean, I know only of one really extensive work on that. It's by Miguel Navasquez and Sandro Popescu. They look at implementing or approximately implementing measurements under energy constraints, in the sense that where you can also quantify how much energy you have to invest to get a decent level of approximation.
I see.
So that's sort of complementary to what you're doing here.
Yes. Okay. Yeah, I see. But in that case, if we consider individual process, the cost of energy of measurement is not so high, I think.
So to explain that, their idea is that you can only do things which commute with the Hamiltonian. I mean, this is sort of fundamental. So you need ancillas, which cost energy to do things that.
Measurement, of course.
Yeah.
It is better to consider this one, but maybe at least in this situation, the cost of energy is not so high, I think. How do you think? Because the individual measurement is not so difficult. Sorry. but not solution. My answer is not so exact. Sorry.
Well, maybe we should save a more exact answer for discussions afterwards, and maybe we should thank the speaker again. Okay, so that concludes the talks for today, and now we go to the poster session. Oh, in 1 second.
Sorry, I just want to quickly remind everyone that if you want to go to David Wineland's public lecture, you need to register. There was an email sent out about this yesterday, so read the email and reply to the email address you need to reply to if you want to attend. Thank you. Enjoy the poster break.